All right, we're going to graph the parent graph, absolute value. So we've got the equation y equals absolute value of x, and these parentheses, the straight ones, are the absolute value symbol. We're going to pick the x value, and I'm going to pick some easy numbers here, -3, -2, -1, 1, 2, 3. We get to pick those, and then we put those into the equation. Absolute value of -3. How far away from 0 is -3, and that is 3 away. -2, absolute value is 2, and so on. Absolute value of 1 is 1 away. And we can make more points, but that'll be enough. So if we go to our graph and graph those points, -3, 3, 0 is here, -3, -1, 2, 3 in the x direction, and 3 in the y direction is right here. -2 in the x, and +2 in the y. -1 and 1, 0, 0, 1, 1, 2, 2, 3, 3, and so on. Now we only did a small amount of points, but there are an infinite amount of points. So I'm looking here, over 1, up 1 every time. It goes 1, 1, 1, 1, 1 every time is the slope. I'm going to continue that on, and the arrow means that it goes this way forever. Other side, same story in the other direction. And there's the absolute value graph. Now, one of the names, one of the vocabularies you need to know is this point right here where it turns. We're going to call that the vertex. Okay, I've switched over to the computer to make this a little bit easier. This is the same thing I did on the paper. This is the absolute value equation. This is the same table of points. And this is the graph that we created. And you can see it makes this V shape. And the line continues to go up forever. In fact, if I zoom out, these will just keep opening up and out forever. But I mostly care about the points down here closest to the vertex, which is this point right here. Now, next, we're going to talk about what happens if you add a number to the end of this. Notice that the +1, I added +1, and it's on the outside of the absolute value part of the equation. And the effect that had, notice here, well, at this point, it used to be here, and now it's here. It moved up by 1. So if you add 1, all of the points shifted up by 1. See how they no longer match up. They're off by 1. If we change this to 2, it would go up by 2, and so on. So if we wanted the points to match up and be at the right place, what we do by adding 1 is we're adding 1 to the y values. So if I add 1 to this, now it is in the right place. And so the table for all of these points is created by adding 1 to every single y value. And we call this a translation up 1. Or sometimes we can say a shift by up 1. Instead, we do -1, as you might have predicted. That has the effect of moving the graph down 1. Every single point has now been moved down 1. And so -1 here, if we wanted to the points to match up, these are the parent graph points. If we wanted them to be in the right place, what we're doing is subtracting 1 from the y values. That is the effect of the, oops, this should be 1. And -1. Okay, so they're in the right place now. All of the graphs shifted down 1. And if we change whatever number we change this to, that's how far down it moves. Okay, if instead, so we're back to the parent graph. So we talked about up and down. If we want to make it move it right, you would think you would add +1. on the inside here. You think that that should make it move in the positive x direction, but it actually had the reverse effect. It made it move left by 1. It was shifted or translated left 1, even though I added a plus 1 here. And the reason that that is that if we are adding 1 to the x values, they now have to be 1 less than they were before to still have the same number inside here. And so this -3, since we're adding 1, it actually has to be -4 now, since when we add 1, then it'll get us back to -3. And -2 has to be -3 because they add 1 and it turns into -2. -1 has to be -2, -1, 0, 1, and 2. And all of the points have moved left by 1. Okay, and the last translation is if we move it right. Again, it's opposite of the way you think it should work on the inside. I'm going to put -1, and that moves it right 1. It doesn't affect the y values, it affects the x values. And those are the input values. X -3, now, since we're subtracting 1, x only has to be -2, because when we subtract 1, then it'll become -3, and the absolute value of -3 is 3. -2 only needs to be -1 now, since when we subtract, if we were to replace x with -1, -1 becomes -2. Okay, and this would be 0. And 4. So now we can see all the points match up. Everything got moved right by 1. And if we change this, whatever number we change this to, say we want to move right 3, I'm not going to go through moving all the points, but you can see here that the same shape, it's that V shape, is moved right 3. Well, I don't want this here. Maybe I do. Okay, next we're going to explore what happens when you multiply this by 2 or by some number. And if you multiply this by anything other than 1, it changes the stretch. It's called a stretch. In this case, the larger I make this, the skinnier it looks. But what's happening is the points are getting stretched upwards. And so let's go back to 2. I have here my points from my parent graph. And what we're doing by multiplying by 2 is we're multiplying all of the y values by 2. So these should instead be twice as much. And that's what makes it look skinnier, is it's actually getting taller as we do this. So anytime that you multiply by something other than 1, the graph gets stretched out. 6. Okay, and that's if we multiply by things that are more than 1. If we multiply by things that are less than 1, like 0.5, it looks like it got stretched the other way. It got wider, kind of this way, but that's just an illusion. It didn't actually, it actually got squished this way. And that's a vertical, this is a vertical change. A vertical shrink is what it's called. And so instead of these being twice as tall, they actually are half as tall. So this used to be at -3, or at 3 rather, 3, and now it's going to be at 1.5. That the amount that it used to be at is half the amount. And just to show you, here's a comparison. let's do, we'll make this y2, we'll just call it something else. And these were our original points here. There's a lot of things going on in the graph. Okay, so these are the originals. And we can see here that each of these points, it didn't go out, it went down. So it got squished down. This is now 1.5. It's half the distance. This is at 1 and this is at 0.5. And 0 is still going to be at 0. 0.5, 1, and 1.5. So everything is half. And what we did is we just multiplied. This is multiplying right here. We multiplied all of the old y values. These are the original ones by half to get the purple ones, the new ones. So the black that you're seeing on the graph was the parent graph points, and then the new ones here are when we multiply by 0.5. And the last thing that we should talk about is, well, what happens when you make it negative? And let's go back and change our... Okay, so the black ones are the original ones, and what we did is we just made everything negative. It's a flip. Some people call it a flip, but it's technically called a reflection. It's a vertical reflection. This point, it now went down here. And the x value is the same, but the y value is negative. So we should do all the same numbers, but negative, except for 0 is going to still be 0. And so we take the original y values and we multiply them by by -1. And I would put the 1 there. It didn't change anything. But we can leave it out if we want. But just so that you see what we're multiplying by, -1 is how we're getting these numbers. Now, if we change that to a -2, it kind of does not only a stretch, but also a reflection. We would have to multiply this by then not only negative, but -2. So this would be -4 and so on here. And that is a vertical stretch and vertical shrink and vertical reflection. Those are the new vocabulary for this particular unit. Vertical stretch is when it multiplied by more than 1. Vertical shrink is when you multiply by a decimal. And a reflection is when there's a negative right here.